This is a joint work with Roshan, Alberto, and Siddharth. So let's quickly start with the motivation for this work. So we have settings where we have agents who have to complete a stream of tasks, and they don't know what these tasks will be in advance, right? So for example, a task can be to deliver a set of goods from warehouse to a lab. But then we can get another task where, in addition to delivering the goods from warehouse to the lab, some processing happens in the lab and the modified goods go to the factory, right? Now, as in real world, we can have unknown, non-stationary, and stochastic dynamics, right? So for example, in this setting, while the agent is transferring the goods from lab to the factory, it might happen that it starts raining, right? So the agent has to keep into account if coefficient of friction with the road changes. Now another thing the agent has to keep into account is to have some limited budget per task. And I'll explain more in detail what this limited budget is. But our intuition is that we can actively conduct experiments to learn environment dynamics much more efficiently. So I'll just quickly go over the problem setting. So as I said earlier, assume we have n number of tasks. This can come in any order, but they can have different initial and goal states, and they can even have different state and action spaces. But the set of predicates and the actions in are known a priori. Now we also assume access to a simulator whose transition function can change arbitrarily at unknown intervals. We have sparse binary reward settings, so you only get a reward after you reach the goal. So our objective is to maximize the number of tasks that are completed within a fixed simulator budget. And this is in terms of number of steps the agent can take in the simulator. Now, as in when the transition dynamics change, the agent should adapt very fast, and it should also try to minimize the regret over here. So assume an oracle that knows what the exact transition of what the exact transition model of the environment is. Then the maximum reward that we can get, we have to get as close to that as possible and as fast as possible by reducing the adaptive delay. Now to solve this problem, we obviously had some research questions that we were focusing on. So the first one was, can we actively interact with the environment, probably through some sort of experiments, right? Like how to gain more knowledge about the actions. And some approaches use something called random exploration, which I guess everybody is aware of. But if we were trying to see if this kind of exploration can be more deliberative to learn the environment dynamics more efficiently. And of course, we wanted to know if it would be useful to learn a planning kind of model. And we want to know if it is even feasible. And I guess to no one's surprise, since I'm giving a talk over here, the answers to all of them are yes. And we will see how we do that. So a solution was to have this loop of learning a partial model of the environment and do planning using that. And the challenges in this kind of learning and planning paradigm are like how do we generate some simple efficient strategies for learning the model of the environment, because remember that to learn that model we have to explore the state space, and this method has to be systematic, otherwise it will not be sample efficient. And second, is it even worth learning a full model if we can solve the task with only a part of the actions needed to complete the task? Because if we learn a complete model, we might learn like descriptions of actions that might change because the environment is non-stationary. So how do we maintain that balance? So for this, we introduce this algorithm, continual learning and planning. And this is a session after lunch. I won't bore you with all the details of the algorithm. I have a graphical representation of how the algorithm works at a high level. So we have a task, the first task that comes as input, and now we have a model. We can bootstrap a model using some model learning strategy, or we can start with an empty model. But the idea is that we can use this initial model to try to solve a task. And it is entirely possible that we won't be able to solve our task using our initial model because it might be empty or incomplete. So what we try to do here is have an experiment generator that gives us a strategy to explore the environment. And we connect that to the sim, and we just tell what actions the agent should try performing in the sim to get more data about the environment, and using that use that to update the model. Now, an important property over here is this experiment generator. So I'll just go briefly over it because So we had this work in Purips where we were learning the models of for an agent using active querying. So basically, if I represent a probabilistic PDL model as this, so for example, we have an open door action, and we want to identify if hash key is a positive precondition, a negative precondition, or it's not even present in the condition, right? So using the algorithm that we had in that paper, we can generate an automated query that is something like, I give you an initial state, and what would happen if you try to execute this policy. And an important property of this autonomous generation of this kind of query is that if I am focusing on hash key in open door precondition, executing this kind of query will give more information about the correct form of hash key in precondition of open door. So for more details, you can refer to that paper. But the idea was that if we keep taking each of these predicates in each action's precondition of effect in order, our model monotonically improves, right? It becomes more and more accurate as we ask more queries. So now with that basic background of our experiment generator, what we do is we try to learn the representation of some of the actions in the environment, and then use that to try to solve the task. And if it solves the task, then we actually execute those actions in the environment, right? And remember that the environment dynamics can change at any time, so it might be possible that executing some action might not give an expected output, right? So then we can again have this whole loop where we try to call experiment generator again, update the model, and try to solve the task. Now, apart from changes in the precondition or effect of an action, it is also possible that the distribution of effects, like my hand can get more slippery, so I may drop a bottle more number of times, right? So the distribution of effect of pickup action might change. So for that, we get this goodness of fit test, which periodically keeps monitoring if the probability distribution of the effects that I am seeing is what I expect from the model that I have. And if it does not match, I again call the experiment generator to update those probabilities. So that's why we have this nice loop where the task can keep coming. I'll keep solving them using my model. If anything changes, I call the experiment generator to update my model. Now moving on to empirical evaluation, we use 4 benchmark domains from probabilistic tracks of IPC, and in the experiment we were changing the action transitions, and of course with each new task we have new initial state and goal, and we provided limited simulator budget per task. For baselines we had 3 things. One was the oracle, which so this was the true model of the environment. So if you solve a problem using this, you will get the maximum reward. And then we had Q learning, which is the vanilla Q learning. And then we had adaptive case, where we modified our newspaper to work for settings where the domain dynamics change. So after every change, if I'm not getting if I'm not able to solve anything, I learn the model from scratch. And here are the results for one of the domains, first responders. Here, so X shows the performance of the oracle, and as you can see that so these vertical lines are when the transition dynamics changes in the environment, and as you can see, our approach is able to solve more number of tasks as we get them, and the average number of rewards that we get quickly reaches that of what the oracle is able to achieve. And adaptive delay, like how much time it takes for the agent after a change to reach the desired performance, that is also very low for our method. Yeah, and you need not just believe in what I'm saying. For all the domains, we had similar trends. Tire world was kind of thing where adaptive case reached the performance of our approach, but then the domain was very small in terms of number of actions, and the stochasticity was also very less. And not just empirically, even theoretically, we were able to show that in between a stage where there was no change, the stationary portion of the approach, the models that we learn are locally convergent, meaning they iteratively get better. And yeah, with that, I would conclude and show, yeah. So we saw that our method is sample efficient for solving tasks under non-stationarity. And we also kind of showed that it pays off to spend some effort to learn a model of the environment because we get improved efficiency later. And in the future, we are trying to work on the directions where we have some kind of belief over what kind of goals we are going to get or what might change in the environment depending on our previous belief, like previous information about how the task is changing. So with that, yeah, I'm open to any questions that you have.
Thank you.
Yeah.
Thank you for the presentation. Very interesting work. I didn't understand if there is some policy learning involved since you have this reward, or if you are planning just by using the model that you are learning. So are you also learning a policy?
No, the policy that we are generating to, like for the agent to try to solve the task, it does not have any